talking about how to tell whether a function is continuous and how to identify different types of discontinuities as well. So a function f is continuous at a certain point x equals c if and only if the following conditions are true. So again, if and only if means if the first statement is either true or false, the second statement must be the same, must also be true if the first one is true and false if the first one is false. In the other direction, it works as well, where if the second statement is true, the first one must be true, and if the second statement is false, the first must also be false. So it's continuous only if the value of f of c exists, the limit as x goes to c of f of x exists, and 3, those things are equal, that the limit as x goes to c of f of x is equal to f of c. Okay? If those 3 things are true, then your function is continuous and you're good. Now, some functions can be a little weird because they have endpoints, right? So you could have something that looks like this, where you have an endpoint here where it has a value at 0 and then it just goes up, something like the square root of x, right? And it just stops there. Well, continuity at an endpoint, you have a kind of a different test here where you're looking at if it's a left endpoint, as this one is, you look and see, is the limit as x goes to a from the right the same as the value of the function at a? And in this case, it is, right? So we say that it has endpoint continuity in this case. And if you're approaching from, if you have a right endpoint, then you approach from the left, right? So for this one, if I have something like, I don't know, this, you just have, I don't know, a function like this. Is this function continuous? Yes, because it's a right endpoint. If I approach from the left, it equals the limit as I go closer to this point is equal to the function at this point. It wouldn't work for this, right? This side, which is a hole at the endpoint, is not endpoint continuous because this is a left endpoint. So if I take the limit as I approach from the right, you can see that it equals something, but the function is undefined at that point, so it doesn't work. Even if the function were defined, if it were up here, right, then that means that I have this jump discontinuity and this condition isn't true, where these things both exist, but they don't equal each other. Okay, so how do we use this? Let's say that I have a piecewise function. Let's say I have that f of x is equal to 2ax minus 3 in the case where x is greater than 1. And let's say that it equals ax squared minus 5 if x is less than or equal to 1. And I want to know for what value of x can I make this function continuous? Now, if I look at x greater than 1, nice continuous function, right? It's linear. X less than or equal to 1, let's look, sorry, not equal to, let's just x less than 1. Again, nice continuous function. So where might this function be discontinuous? Well, it might be discontinuous at the point where the two pieces connect, right? So what I need to do is I need to set these equal to each other because I need these a's to match. So I'm going to say, let's set these equal at the point x equals 1. So at the point x equals 1, I have 2a times 1, because x is 1, minus 3 equals a times 1 squared minus 5. And I want to solve for a because then I'll be able to use that to make the function continuous. So I'm going to have 2a minus 3 equals a minus 5. Let's add 3 to both sides. So I have 2a equals a minus 2. Subtract a, I get a equals negative 2. Okay, so that means that my function, to make it continuous, I should have the function f of x equals negative 4x minus 3, and I have negative 2x squared minus 5, okay, for x greater than 1 and x less than or equal to 1. Now, this should be fine. Our answer should work. But if you want to check your work and make sure you didn't mess up, just check these 3 conditions, that these 3 conditions are true. Does f of c exist? Well, f of 1 would be equal to, I look and I say, okay, this one is the one that includes 1. If I plug in 1, I get negative 7. So I know that for condition 1, f of c equals negative 7, so it exists. This is a check mark. There we go. For case 2, does the limit as x goes to c of f of x exist? Here we check and see, does it work from the right and from the left? Because I know that the limit only exists if the limit from the right and from the left both exist and equal each other. So the limit from the left is going to be equal to the same thing we just calculated, right? If x is less than or equal to 1, it's negative 7. From the right, we have negative 4 times 1 is negative 4, minus 3 is also negative 7. So that means that the limit as x goes to c from the right of f of x is equal to the limit as x goes to c from the left of f of x, and it equals negative 7. So therefore, this also equals the limit as x goes to c of f of x because they match. So this is another condition that is satisfied. Now the third condition must be that does the limit as x goes to c of f of x equal the value of the function at c? And in this case, it does. Negative 7 equals negative 7. So again, we have our third check mark, and we are all set. So that's how you figure out if something is continuous or how to make something continuous as well. Now, you do have discontinuities, and you've seen a lot of these discontinuities already in rational functions when we studied those. But here we're going to talk about kind of the different classes of discontinuities. Now, depending where you look, people categorize discontinuities differently. There's no real, at least that I'm aware of, like absolute set of discontinuity classifications. People call them whatever they want. So we're going to call, I'm going to go through, I think, 6-ish classes of discontinuities. The first kind being a jump discontinuity. So you have a jump discontinuity when the limit as x goes to some point c from the right of f of x does not equal the limit as x goes to c from the left of f of x. So if you have something like this, right, where you're going like this, then you have a hole, and then you have a hole, and then you have this. Now one of these could be filled in, it doesn't even matter. I could have, this and then this, right? And here, the limit from the right does not match the limit from the left, so therefore we have a jump discontinuity, because you're just jumping right up. Another discontinuity type that you could have is called an infinite discontinuity. Infinite discontinuities occur when you have vertical asymptotes, okay? So for the most part, you can have, they both go up, right? From the right and from the left, the function goes just up to positive infinity. And in this case, the limit would be infinity. You could have the case where they both go down, and because then they're both going down from the right and left, you'd have negative infinity, so positive infinity, negative infinity. Or you could have a case where one side goes up and one side goes down. It doesn't matter which side goes up, which side goes down, but that means it's infinity from the one side, negative infinity from the other, and here your limit is undefined, does not exist. But this is called an infinite discontinuity. Okay. The third kind is a removable discontinuity. A removable discontinuity is also referred to as a hole. So if I have something that looks like this, right, where it has a hole here, or maybe it has a hole and it has a point here, okay, this is considered a removable discontinuity. So the function, let's say if we call this point c, right, f of c exists, but f of c does not equal the limit as x goes to c of f of x. And, this also exists. So the limit as x goes to c of f of x also exists. Okay, so they both exist, but they're not equal. So these are the three that are the most common types of discontinuities that you're going to encounter. And, you can tell what kind you have by using the tricks we learned from rational functions. If you have something kind of piecewise, that's probably going to be a jump discontinuity if there is a discontinuity. Vertical asymptote is going to often give you an infinite discontinuity, and a removable is going to be where you can cancel out something in the function and you have a hole. Okay. There are other kinds, even though they're a little bit less common. So I'm going to get these out. These are the three again that are really important to know. But then we get to some others. So you could have something like a mixed discontinuity. A mixed discontinuity is anything where you have a mix of two or more discontinuities. So if I have something that looks like this, where from the left maybe it goes to infinity, and from the right I have a hole at this asymptote, and then it just goes like this, or it just goes like this or something. This would be a mixed discontinuity. Do that, okay, because it's got both a hole and an infinite. Another discontinuity you can have is an oscillating discontinuity. So the best example of an oscillating discontinuity is if you were to graph the function f of x equals the sine of 1 over x. Now, I highly recommend you try graphing this on Desmos, your graphing calculator, or another kind of graphing software. But essentially what happens is, so sine is stuck between 1 and -1, right? Well, sine of 1 over x, so it starts out reasonable, but then as you get really close to the 0, where sine of 1 over x, we can't use 0 as an input, it's going to be undefined there. It starts oscillating so rapidly that you pretty much fill in every single point between, that you just can't even see it anymore because it's oscillating so rapidly. So this is called an oscillating discontinuity. And finally, we have what's called a pathological discontinuity. Pathological discontinuities are just discontinuities that are so crazy and wild that you just can't group them anywhere else. For example, if you have the function f of x equals x if x is rational, and we'll say 2 if x is irrational. So this, if you graph this, this is a wild, wild function, because what you essentially have is you have one actual physical dotted line that goes like this, but like dot is too straight. It really is just points. You have a bunch of points along this line in one direction, and you have a bunch of other points along this direction, like this. And this whole thing is just wildly discontinuous. It's continuous, I believe, at only one point, and everywhere else it is discontinuous. So this kind of thing, which is just like, it doesn't even resemble a function, it's just a bunch of points kind of strewn together along lines. This would be a pathological discontinuity. Okay, so those are the kinds of discontinuities that you'll see. Again, the first three are the most important, but that wraps up continuity and discontinuities.